Hey everybody. So as promised, the last week of class is going to be on regression. Just a couple of disclaimers before we dive into this. Regression is normally a semester-long course, and we're going to be providing a condensed, shortened version here. If it's something that interests you, I definitely encourage you to take the next level statistics course and learn it more thoroughly. There's a lot of applications and modified ways to do regressions besides what I'm going to show you now. To start, I want to do a review of simple linear regression, which you might also know as univariate regression because you're just regressing on one variable. And then we'll talk about multivariate regression and its parallels. We'll go through an example in JUMP. We'll talk about the sum of squares, which is related to the sum of squares that we did in ANOVA. And then we'll go over assumptions checking because regression is a really powerful and useful tool, but a regression model, while being really easy to build with statistical software, is only useful when it's valid. And it's really important that you check assumptions and make sure your model is valid before sharing out results for all the reasons we talked about at the beginning of the semester. Your results won't be reproducible if your model's not valid, so that'll be what we cover in the second lecture regarding regression is those assumptions in more detail. So let's start by reviewing simple linear regression. We covered this many lectures ago when we talked about correlation. You might also hear some people refer to regression more generally as least squares estimation, and the reason for that is because the solutions that we're going to cover, which you see them here for simple linear regression, are derived by minimizing this sum of squares. And if you remember, y hat just represents your predicted values for your response, and y is your actual values for your response. So you could do some calculus to minimize this equation, and you will find that these are the values that minimize the equations. You might be thinking, well, where's beta 1 and beta 0 come from? This is just in terms of y's. Well, the y hat can be written as beta 0 plus beta 1x, right? That is our predicted value. And this is a form you've seen many times before. To repeat what we talked about last class, y in algebra is often written as mx plus b, where b is your y-intercept and m is your slope. In statistics, we just use slightly different notation where we write beta 0 to represent the intercept and beta 1 to represent the slope. And that'll make more sense when we talk about linear regression and we switch from scalar form to vector form, which, don't worry, if you're not familiar with matrix algebra, we're not going to derive anything. But that's the reason we use beta 0 and beta 1 is because this turns into a vector with multiple betas in the event that you have multiple x variables that you're regressing on. So these were the solutions to the least squares equations for univariate regression. I should say sometimes you'll hear people refer to it as bivariate regression because they're including the y or outcome or dependent variable as one of the two. However, I find it helpful to think of it as univariate, sorry about that, because you're just looking at one variable being regressed on your response. So these are the solutions and how you derive them manually. We talked a little bit about these. I don't want to say sum of squares because they're not sum of squares, but they're this is like your covariance between x and y, and this is essentially your variance of x. But don't worry, you don't need to know how to derive it by hand. We will do an example in JUMP. So let's go to the multivariate regression, and you'll see the parallels here. So again, you're still minimizing this equation. The difference is we tend to treat y as a vector, so the interpretation between y is slightly different. Again, you don't need to know that for the purposes of this course. But your regression equation also looks slightly different, right? Because now you have your y-intercept and you have several variables being regressed on different x's. In fact, each of these x's should have an index as well, x1 to xk, if you're going to write it in scalar form. But more commonly, it's written in matrix form, where x is all of your independent variables. Each column is one independent variable. Beta is your beta vector, which should actually not be capitalized. That's a typo on my part. And then you have an error, just as before, creating noise above and below your regression. In this case, in 2 dimensions, it's a plane, but your predicted values. And I know this is a little intimidating in terms of notation, but if we flip back to simple linear regression, right, we had a line which is represented by this equation. We have our actual data points above and below that line, and the error is just the noise around that. Whereas in multivariate regression, well, bivariate in this case, because you can see there's 2 variables, 2 independent variables, crime rate and number of rooms, which is being used to predict the value of homes, specifically the median value of homes in thousands of dollars. And you can see there's this plane that goes through it, and then a bunch of noise separating the actual data points from the plane. It seems to be randomly scattered, which we'll talk more about when we get into assumptions. And this is the solutions to multivariate regression to get your beta vector, which will be made up of beta 0, beta 1, and so on, all the way to beta k, where k is the number of variables in your multivariate regression. You don't need to know how to derive it. We're gonna use software for this, but I just want you to be aware the solutions look slightly different than in univariate equations, where they're just algebraic equations in scalar form. And what I mean when I say scalar form, it's just that it simplifies to a number as opposed to a vector, which is a sequence of numbers or a series of numbers, not necessarily a sequence. Okay, so let's do an example in JUMP. Before we do an example in JUMP, I have an example that I want you to think about. So if you're predicting weight from age, sex, and height, which predictors do you think are going to be useful? We're going to do a very similar example in JUMP, and I'm going to show you how to evaluate the usefulness of those predictors. Okay, so this is a data set that you could get from going in Help in JUMP and clicking on Sample Data Folder. And I got this big class data frame, which we'll go over, which is really useful for making predictions because the variables are helpful. So obviously names are not going to be helpful, but we talked about making predictions on weight, and some variables we were interested in looking at is age, gender, and height. And there's good reason to believe that each of these has some impact on weight. And the procedure for doing this is actually very similar to what we've been doing in our inferential tests. Most of all of our inferential tests, we went to fit y by x because it was univariate. In this case, to do regression, you say fit model. You could still do a univariate model, but let's go over how to do that. So you put your outcome variable in the y box, which we said we were interested in predicting weight. And let's just start with just 2 variables for now. We know height is going to have some effect on weight, intuitively, causally, right? This is something that we believe. So let's put height as one of our variables, and then let's put gender as our second variable. So this is where your independent variables will go. And then you can see it's referring to how you want this model to run, and we're doing least squares. That's all we're going to cover in this class. And you click run, and you get the output of your regression. Some of these we're not going to use, but I want to go over a few aspects of these results. So let's ignore the leverage plots for now. I don't think we're going to cover that in this course. But this is the regression plot. And in this case, because it's univariate, it's something you're really used to seeing and interpreting. Here's weight and here's height, right? Because there's only two variables included. I'm sorry, it's not univariate, it's bivariate. So they just did not include sex or gender. And the reason for that is because it's categorical, and you can split the line essentially by each of those categories. So you're seeing, female in red and male in blue. And that's kind of your two regression lines for each category. It would have been nice if they colored the points as well based on the gender they belong to. But this regression plot will change if you have multiple numeric variables. Instead, what you'll see is your predicted value versus the actual value. And the reason for that is, as you saw in the slideshow that I just presented, as you have multiple numeric values, you're not really looking at a line anymore. You're looking at a plane, or even something more complicated in the event that you have more than two independent variables, and it can be harder to interpret. You could do several plots, and that's another option, one for each variable. But it is going to vary based on the type of variable, and it's more information to digest. So what you'll commonly see instead is, these are my predicted values and these are my actual values, and what you want to see is a line going through them, meaning there's like a one-to-one relationship. But of course, you're never going to get a perfect fit, and there's going to be some noise above and below that line. However, in this case, it is much easier to interpret. We see like men tend to have a lower weight, which is a little surprising, than females, slightly lower, at least in terms of what we predict. And this isn't a huge amount of data, so we'll have to see how this plays out. And as we expect, as your height increases, so does your predicted weight, and we see that kind of trend in the scatter plot as well. And this is what I was talking about before with the actual versus predicted. This is more commonly what you will see when you have multiple variables. And it's doing a pretty good job, because like this is the line indicating a perfect fit, the y equals x line. And you can see most our points are close to that line. We have more noise in the middle, but also more data in the middle. So this is another helpful measure of how useful our model is. Now I want to talk about the individual variables. When you thought about this question earlier when I posed it to you, you probably assumed that height would be important. So let's talk about how we identify which variables are important. And we'll go right here to our parameter estimates. And the interpretations of these are different because you're regressing multiple variables at a time. So here's height. We see an estimate of 4. What does that mean? That means that for every 1 unit gain in height, and if we look at our height in our data set, it'll tell us, but it looks like it's measured in inches here, right? Because 60 would represent 5 feet. Most people are between 5 and 6 feet. So it looks like every inch in height, in terms of your prediction, not, there's going to be noise in addition, but in terms of your predicted value, corresponds to an increase of about 4, and the units we're talking about in weight looks to be pounds. So for every 1 inch gain in height, it corresponds to about 4 pounds. And we see that that's highly significant here. And this is something I want to talk about. So what this means is that the beta for our height variable is about 4, and we measure significance by whether or not that beta value is 0. What I mean is, let's just say there was no relationship between height and weight. We know intuitively that there is, but let's just pretend for a second that there isn't. The scatter plot would just be random noise. There wouldn't be a upward trend like there is, and the regression line would be flat, because your best guess is your average all the way across height, because we're assuming that it's not helpful. So what does that mean for your slope? Well, what's the slope of a flat line? It's 0. It's not helping you to make a prediction if there's no relationship. So that's what's being tested here. We get our measure of center is 4 for the effect of height on weight. However, another way to think about it is that how different is that from 0, which is what we expect to see if there is no relationship. So we look at our standard error, and just like always with our t-ratio, we take our estimate, divide by our standard error, and get our t. What does this t correspond to? In terms of the p-value, it depends on the degrees of freedom, which we don't need to get into, but we will talk about a bit in when we get to sum of squares. But you can see they do the math for you. The probability of having a t larger than magnitude of what you observe, larger in magnitude than what you observed, is essentially 0, right? This is very close to 0. It's 0.01%, which is telling us that height is hugely influential in predicting weight. And more specifically, the interpretation is that as height increases, weight increases by about 4 units, or 4 pounds, I should say, which is our measure of center. However, you could also think about it as it's significantly different than 0. And this has kind of like a one-to-one correspondence with the confidence interval, which is something that we didn't talk about when we did inferential tests, but it's something that I want to now that we've covered confidence intervals. And what I mean by that is that so if you were to construct a confidence interval, you take your critical t statistic, multiply it by the standard error to get your margin of error, and add and subtract that from the height. If the resulting, not your height, from your estimate, your point estimator, right? And that's how you build a confidence interval. Your resulting interval will not contain 0. And we know that because, well, first of all, you should see intuitively that a t statistic of 6 is far away enough from 0 that it's not going to, that it's much larger than whatever our critical value for the t distribution with the associated degrees of freedom would be. However, another way to think about it is through our p-value. So if 0 is contained in our confidence interval, that tells us that our p-value is going to be greater than alpha, because 0 is contained in that confidence interval. In this case, p is less than alpha. And remember, alpha is being reflected in the t statistics in the critical value of the t distribution, which we're multiplying by our standard error. So we are accounting for alpha in our confidence interval. If that confidence interval doesn't contain 0, we will get a p less than alpha, we will get significance. If the confidence interval does contain 0, we will get a p greater than alpha, indicating that there is no significance to our point estimator, or it's not significantly different than 0. So there is that kind of parallelism in approach, whether you choose to construct a confidence interval or build a t-ratio and calculate the p-value, the interpretation or the results, the way you would interpret those results is similar in terms of determining if height is significantly different than 0. Okay, so we talked a little bit about height, which is numeric, so it's like easier to interpret. Let's talk a little bit about sex. So that's a different interpretation because it's categorical. And you'll notice that instead of just writing the variable name, they put these brackets with an F in it, indicating the level, the category that it's in, that's being assessed in reference to the holdout. What I mean by that is a categorical variable has several levels. So in this example, we're talking about sex or gender, which this is an oversimplification, of course, for the purposes of this model. It's assuming just 2 genders, male and female. And so female is the effect that's being measured in reference to the holdout. And I know there's only one holdout because if there were more, they would have listed them all out, as you'll see in a future example. And in this case, they only list female, which tells me that the holdout, the baseline, the reference level, whatever you want to call it, is male. So what this is telling me is that females tend to be about 2.2 pounds heavier than males. Again, this is a point estimator, so there's a degree of uncertainty associated with it, which you get by taking your standard error and multiplying it by your critical T statistic. And you can see that our p-value here does not duck alpha. That doesn't mean that there's not a relationship. It just, to reiterate what we've been talking about with hypothesis testing, this means we don't have enough evidence that there is a relationship. And you could do a quick sanity check here by looking at this plot, and we see the female category is indeed about 2.2 pounds higher than the male category. So that's how you would interpret a categorical variable. This is the simplest case where there are only two levels. Again, it's an oversimplification. We know that there's more than two levels to gender, but in this example, this is sample data that's been provided by JUMP that's pretty outdated. They just gave us two levels for this category. And in this case, we have an estimate of 2.2, meaning that females are 2.2 pounds heavier than the holdout or baseline, which is males. But it's not significant, and that is in and of itself a finding. It is not significantly different than 0, which in terms of hypothesis testing is telling us that there is not a significant difference between the weight of females and males, at least in the data we have so far. Maybe if we collected more data, we would get different results. But at least according to the amount of data we've collected, there's not a significant difference. Whenever you get a result like this in your parameter estimates with insignificant variables, I want you to rerun the model only including your significant variables. Okay, so we talked about height, we talked about sex or gender, we did not talk about the intercept. So the intercept is more straightforward, I think. This is your beta 0 term, right? And the interpretation here is kind of silly, right? Because it's the value of weight at a height of 0. Well, what's a height of 0? It doesn't really make any sense. And neither does a negative weight, right? So this is kind of silly. And this is where the assumption of linearity kind of breaks down, right? Because we know that weight is not quite linear, right? As your height increases, first of all, there's no 0 height to be had. So like the range of values is an issue in and of itself. But then on top of that, your weight doesn't increase linearly. And you can somewhat see that in the scatter plot, even though this data, it does look actually fairly linear, because we're looking at this range of heights, which is like 4 feet to like 6 and just about 6 feet. So within this range, it might actually be linear, and that's what I'll bring in another important concept here. That's the idea behind extrapolation. So you'll hear people say things like, don't extrapolate beyond the range of the data you've collected, and that's an important distinction here, right? You don't want to predict values that are less than 52 or greater than 70 because those data points weren't used to construct the model and may behave differently than what we've seen so far. So extrapolating just means going beyond the scope of the data used to build the model to make a prediction and assuming the same model will hold. Okay, so I know I threw a lot of concepts at you, but to refresh, there's two plots here that I wanted to go over. This is the regression plot, which really you only want to look at one variable at a time for, and then you have your actual versus predicted, which generalizes across all your predictors, and you want to see the data lying roughly along this y equals x line. Secondly, we talked about parameter estimates and how to interpret those. I'll change up the order a little bit. The intercept is pretty straightforward. You want to remove anything that's not significant. Obviously, removing the intercept is not something we typically do, even if it is significantly different than 0. But your independent variables you could remove if they're not significantly different than 0 because they're not adding to your model. And one complication you may have heard of in regards to regression is this idea of overfit. So the more variables you add to your model, the better it'll predict, according to some criterion. There are criterion that fix for this, but the better it'll predict. Not necessarily because the model's more accurate, though, just because those free variables are able to capture some of the noise that doesn't represent the underlying trend of the data, which is just like a somewhat convoluted way to say don't add extra variables, extraneous variables to your model. It'll look like it predicts better, and that'll make more sense when we talk about sum of squares, even though the reality is that those variables were not helpful. So rerun the model, removing gender or sex because it's not useful in making these predictions. It's not significantly different than 0, and it is explaining some of the noise and variation that isn't necessarily part of the model. You might have heard people say things like a statistician's job is to separate noise from signal, right? So signal, in the case of regression, you could think of as like the regression line, the underlying model, with the noise being the distance between your values and the regression line. So you could think like with some more advanced math, we could fit like a curve that goes through all of these points, right? And that would be a really poor job of separating noise from signal, because we're basically saying there is no noise, right? And with this model, we can perfectly go through every point. However, as you get new data, it's not going to fit your model very well, and we know that because there is an element of noise to this, no matter how many variables we plug in. That's one extreme. The other extreme, which I was just talking about, is so that's the extreme of overfit, where you're just adding, one way to overfit is to add variables, add more wiggle to your line, but it's not necessarily capturing the underlying trend or signal. It's just taking the noise in your data and attributing it to the model. Okay, so we're going to stop at this simple example for now, and next lecture we're going to dive into age, which JUMP treats a little bit differently than you might expect, and we'll start to look at that sort of data.